Well, hello and welcome back to another episode of Quantitative Bites. It's great to see you all. I hope you're doing well. So today I wanted to continue with the series of videos where I've been looking at implementing various mathematical techniques in C++. And in particular in this video, I want to focus on creating a class that will allow us to work with matrices. Of course, matrices are, some would argue, the essence of linear algebra and really are incredibly important to a great many fields of science and engineering, and in particular a great many aspects of scientific computing. So initially what we're going to look at is creating the basic functionality of a class to handle two-dimensional matrices, and we're going to implement just the basic arithmetic operators of addition, subtraction and multiplication. And in subsequent videos we'll go on to look at creating code to do more complicated things, but for this video today it is sufficient really to limit ourselves to basic matrix arithmetic. So I'm going to begin with just a very short introduction to basic matrix arithmetic and how that works, just to make sure we're all on the same page, and then we're going to jump right in and actually look at the code that I've created so far to create a class for handling two-dimensional matrices. Now, as with all of the code that I show on this channel, this is code that I've created to solve a particular problem that I have, so I've created the code that is appropriate for me. The way that I've gone about solving the problem may not be the best way of doing it for you, depending on what problem it is that you're trying to solve. If, however, you do decide to copy the code that I have used here, of course you're free to do that. But I would encourage you to make sure that you test it thoroughly yourself first. Of course I make every effort to ensure that I don't make any mistakes in my code and that it's free of bugs, but I can't obviously guarantee that that's going to be the case. So do be sure to test it thoroughly yourself if you're really going to use it for anything. Otherwise, I really just hope that the code might be inspiring and might encourage you some of you out there to go and create your own code to solve these kinds of problems. Anyway, without much further ado, I'll just say, as I always do, that if you like this video, please hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to post a video roughly once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Okay, let's go and have a look at basic matrix arithmetic and how we can make a class to implement these basic operators. Okay, so I thought I'd begin with just a very simple overview of basic matrix arithmetic, really just to make sure that we're all on the same page, so that when we come to look at the code in a moment, it should be clear exactly what it is that we're trying to implement. This isn't going to be any kind of an exhaustive review of matrix arithmetic or anything like that. I really just want to go over the real basics. I want to talk about addition, subtraction and multiplication, just to go over that. Apologies if you are familiar with this stuff already. So matrix addition is really simple. If we have a matrix A here coloured in orange and a matrix B in blue, plus A plus B equals C, so we've just put these as two square matrices like this. So we have our matrix A is composed of A11, A12, A13 and so on down to A33, and the matrix B is composed of B11, B12, B13 down to B33. Obviously. So what would C equal? Well, it's really very simple. C is simply composed this way. So these are both 3 by 3 matrices, so the result is going to also be a 3 by 3 matrix. The first element is simply the first element of A plus the first element of B. The second element is the second element of A plus the second element of B, and so on. That's pretty straightforward. That's matrix addition. Needless to say, subtraction is exactly the same. We just replace the plus with a minus. So implementing matrix addition and matrix subtraction is going to be very easy. So the one that does need just a little bit more talking about is matrix multiplication, which is perhaps not quite so straightforward. So matrix multiplication is not done on an element by element fashion as we do for matrix addition and matrix subtraction that we've just seen. So if we talk about multiplying our matrices A and B together, now notice here A and B are slightly different. So we have our matrix here, which is composed of 3 rows of 4 columns, and we have our matrix B here, which is composed of 4 rows of 3 columns. And if we multiply those together, our result C will be composed of 3 rows of 3 columns, so the result will be a square matrix. And the way this works is that for the first element of C, C11, we consider the first row of the matrix A along with the first column of the matrix B. Okay, and what we actually have is that C11, the first element here of the matrix C, is equal to A11, the first element of A, multiplied by B11, that's the first element of B, plus A12, that's the second element of A, multiplied by B21, so that's the second item in the first column of B, as we see there, plus A13 multiplied by B31 plus A14 multiplied by B41, and that gives us C11. Okay, C12 we do exactly the same, except now we take the first row of A and the second column of B, and we calculate C12 in exactly the same way. And C13 we do the same thing again, we take the first row of A with the third column of B, and that gives us C13, and we just keep going in that way. So C21 we take from the second row of A, now with the first column of B, and then C22 we take the second row of A, now with the second column of B, and so on. I think you can see how that's going to go. And that's the basic process that we're going to implement for addition, subtraction, and multiplication of matrices. So one thing that I want to talk about as well is exactly the way that I've decided to go about storing the data. So I'm creating this class really only for handling two-dimensional matrices. For the moment, that's really all that I'm interested in, and that's what we're going to work with. Now, the standard way of creating a two-dimensional array in C++ is to implement something like this. You might do matrix array equals new, double, and then you specify the size of each dimension in square brackets like so. The problem with doing that is that we can't do something like this. So if we don't know at the time that we're writing our code what size the matrix is going to be, so we need to represent the number of rows and the number of columns with variables. And that doesn't work. If we write a line like this in our code and we try to compile that, we'll get an error because it will complain that the size of the array must be a constant. However, it is possible to do something like this. So we can do matrix array equals new double n elements, okay, where n elements is obviously equal to the number of rows multiplied by the number of columns. So what that will give us is a single linear array that we can use to store our elements. Now, I know it's possible to do this kind of multi-dimensional array by storing pointers to arrays, and in fact with this syntax here this is exactly what will happen. See, the compiler will deal with that by creating an array of pointers where each pointer points to a single one-dimensional array, and there are ways of setting this up in loops in order to create two-dimensional arrays where the number of rows and the number of columns are not constant. However, I find that a little bit cumbersome and I prefer not to do that way. Another way that might be a good way of doing it would be to use the vector class from the standard library, and then you can create a vector of vectors essentially to represent two-dimensional data. But again, for simply dealing with what are mostly, in my case, going to be quite small matrices, that really seemed overkill. So again, I didn't really want to do it that way. So I've opted to go with the sort of classic way of dealing with allocating arrays in C++ using the new keyword. Of course, wherever we use the new keyword, we do have to be very careful to make sure that we delete the array that we've created to free it from memory when we finished with it. Of course, C++ doesn't have any form of garbage collection or anything like that that you might get with other languages, so we do have to make sure that we remember to do that ourselves, which is quite easy to do when we're working with classes because we can simply put that code in the class destructor. Okay, so the real question then is, if we're going to store all of our elements as a linear array, how do we index into that array using row and column references? Well, this is the array that we're talking about. So as an example, so we have A is simply a 3x3 array, like so. Now what we're actually going to do, we're going to store that linearly in as a linear array like this, organized as A11, A12, A13, A21, A22, A23, A31, A32, and A33. Now it is important that we are consistent with how we're going to order these elements, because obviously if we do it one way in one part of the code and another way in another part of the code, then quite clearly that's not going to work everywhere. So we have to be careful to do it consistently. And now we can actually, to index into that, given a row and column reference, we use a formula such as this. So we're simply going to use linear index is equal to the row that we want multiplied by the number of columns plus the column. And that's really easy to see how that works. If row and column are both 0, so we want 0, 0, that would be the first element. We see we have 0 times the number of columns, which in this example is 3, so 0 times 3 is 0, plus 0 is 0, so linear index is 0. We know we want A11, the element at index of 0 is 1, 1. If row is 1 and column is 0, number of columns is 3, so row is 1 times 3 plus 0, of course then linear index is 3. Okay, so row 1, column 0, that is going to give us a 2, 1, and we see linear index of 3, you have 0, 1, 2, and 3. It's that one is indeed a 2, 1. If row is 1 and column is 1, numcols is of course still 3, so now we have 1 times 3, which is 3, plus 1, which is of course 4, and we should now be getting a 2, 2, and now we have 0, 1, 2, 3, 4, would give us a 2, 2, which is the correct element. So we're going to use this strategy for indexing into our linear array, and we're going to store, for the reasons that I've just described, all of the data for our two-dimensional matrices as a simple one-dimensional linear array as shown. Now, if anything of that doesn't make any sense, hopefully it will become clear when we come to look at the code. So let's jump in and have a look at the code right now. Okay, so now there's a few things here to talk about. So this is the code that I've implemented for what I've called the QBMatrix2 class, and I've put all of this code into one file called qbmatrix.h. Now there is a reason for that. Normally I would divide the header file and the CPP file, so I would have the header file simply to define all of the prototypes of the various functions and everything in our and members of our class, and then I would put the actual implementation in a CPP file, and that is really the way I prefer to do it. Now the reason I haven't done it that way in this case is because I've decided to create this matrix using templates. So as you can see here, before the class definition we have this syntax here, template class T, and the reason to do that is I didn't want to hard code a specific type associated with this. I want the user to be able to create matrices corresponding to any particular data type. So they can create a matrix of integers, or they can create a matrix of doubles, or a matrix of singles, or actually really whatever they want. Obviously really only numerical values are of course going to make sense, but in principle I suppose you could make a matrix here of anything. And when you do that, when you use template this way, because the compiler, when it works, when the compiler comes across an instantiation of the class in your code, it will then create the class according to the data type that's associated with it at that point. And because it doesn't know that in advance, it needs to have access to all of the code in one file. For reasons I'm not entirely clear about, the compiler isn't able to look into the CPP file corresponding to the header file when we do it this way. So to the best of my knowledge, this is really the only way to do it. We have to bring everything together into the one header file, which isn't really a problem. It's just, it does go against how I prefer to do my code, but it doesn't really matter. It's perfectly feasible simply to put all of the code into the one header file, which is what I've chosen to do. So let's have a look through the code. So we're in the header file, so of course we start with the if-and-def qbmatrix2_h, the include guards, standard syntax, and then of course we have, as we've just described, our template syntax here, which gives us a variable t, which now represents whatever data type we're going to use, and then we begin our class definition of QBMatrix2. I called it QBMatrix2 because it is specifically for two-dimensional matrices. At some point in the future I may well look to create a class for handling n-dimensional matrices, but for now I'm only really interested in 2 dimensions, so that's what we've done. So we define a bunch of public methods first. We have various constructors. We have of course the default constructor that accepts no input parameters. We then have a constructor that accepts as 2 integers representing the number of rows and the number of columns in our matrix. And then we have a constructor that accepts the 2 integers as input here, number of rows, number of columns for the size of the matrix, but then also accepts a linear array that contains all of the data that we want to store into that matrix. And this is the first place where we see that we've used this t. So this t comes from here, it's from template class T that we have here, and we put T here because we don't know what data type this is going to be. So if the user has specified they want a matrix of doubles, then the compiler will replace T with double. If it's a matrix of singles, it will put in single, whatever, or integer would be int. So the compiler will take care of that for us. So all we have to do is write const T start input data, which means we want a pointer to our input data, a pointer of type whatever T is, to our input data as a linear array. Hopefully that will become clear as we go on anyway. And we then also have the copy constructor, which accepts as input another instance of the QB matrix 2 class. Notice also that this has to be of type T. Wherever we create an instance of the QB matrix 2 class, we have to specify what type it will be. The copy constructor, we assume we're only going to be copying matrices of the same type, so we simply put that will be an instance of QB matrix 2 of type T as input to the copy constructor there. Okay, we have a destructor. We need that because we're going to be dealing with memory allocation, so we have to make sure that we free up any memory that we've allocated as we go. We then have space for configuration methods. Currently we only have one, which is a resize function, which allows us to change the size of a matrix at any time. It returns a boolean representing whether or not the process was successful, and accepts as input the number of rows and the number of columns. And we then have methods to access the elements of the matrix. So we have getElement, which accepts as input row and column indices as integers, and it returns a variable of type T. So as before, we don't know what type that is going to be, so we have to use the T reference from here, and that will return an element of type T. We then have setElement, that is basically the same syntax really. It returns a boolean whether or not it was successful as row and column as input, and element value as before of type T. And we have functions to get number of rows and get number of columns there that don't need much describing for those. And now, in order to implement the basic arithmetic that we've just been talking about, we overload the various operators. So the first that we'd have is we overload the equality operator equals equals. It's used to test for equality, so we can use this to compare two matrices to see if they're equal. Obviously this returns a boolean. We're referencing the operator equals equals, and it accepts as input a const QB matrix 2 of type T, and a reference to that, a pointer essentially to that which we're calling RHS for right hand side, so that represents the right hand side of the operator. Okay. Now, where it gets a little more interesting is where we need to overload the plus, minus, and multiply operators. Now, first of all, we have to define these methods, these functions, as friends of the class. Okay, so the definition of the functions that are going to overload these are not actually going to be part of the QB matrix 2 class. Even though we're defining them here, as you'll see when I come to that part of the code, we don't actually define them as belonging to the class, but we state here where we define the prototype that we want them to be friends of the class. Now, the reason we have to do that is because they have to have access to the private members and functions of the classes, or the instances of the classes that are being referenced when we use the relevant operator. And the way to do that is to declare them as being friends. And notice also that where we define these as friends, it's necessary to create a new template variable, which I've simply called u. So we have a new definition for each of these, a template class u, and then we are looking at friend of type into an object of type QB matrix 2 of data type u, and well, so on. And then you can see the various syntax. The input to each of these is going to be simply two matrices, either QB matrix 2 u reference left hand side, and const QB matrix 2 of type u reference right hand side, and so on. So fairly similar syntax for those. The only thing to note is that the reason there are three definitions for each of these operators is because we have to handle separately the different conditions. So considering just addition, we have a condition where the user wants to add one matrix to another matrix. We have the condition where the user wants to add a scalar to a matrix, and we have the condition where the user wants to add a matrix to a scalar, and similarly for subtraction and similarly for multiplication. Okay, so we know that matrix by matrix multiplication is a little bit more complicated. It's not done element by element. We've just seen that, and we'll see the code for that in a moment. But then when we come to multiply by a scalar, then that's actually quite trivial. And finally, we have just one private method, which is called sub to ind, and this converts a subscript into an index. So the idea of that is to take the row column values here, row and column, and return the appropriate linear index for that. And then in our private method, private members, we simply have a pointer to an array for the matrix data, of course, of type T, and we have integers for the number of rows, the number of columns, and the number of elements. And then from there, we just move on. We actually have all of the functions are declared in the header file. So for the reasons that I've already described, we now have all of the functions declared in the header file. So that's the end of the class definition there. And then we move on to actually define all of these. So the constructors are defined, all these functions as belonging to the QB matrix 2 class. And note that for each definition, we begin now with this template class T, and then we refer to any data types that we need of type T. So the default constructor, which accepts no inputs, it does create a pointer for the matrix data, as it will just be a one element array. But you can see the syntax here. So we have m underscore matrix data equals new T, then square brackets and the number of elements. And this is simply because at the time of writing, we don't know what the data type is going to be. So as before, for the class definition up above, we represent our template for whatever the data type would be by T. So wherever we write T, that will become substituted when necessary by the relevant data type. So, and then we have the next constructor, which simply constructs an empty matrix, all elements equal to 0, based on n rows and n cols. And then we have this one that accepts a linear array as input. So we talked about that just now. The code for this is very simple. It just stores the number of rows, the number of columns, calculates the number of elements, defines the array for the matrix data here using new T m underscore n elements, and then we simply loop through all of the elements, and we simply set the ith element of matrix data equal to the ith element of input data, and that's it. Note that, of course, we are assuming here that input data is of the right size. We assume that the user has taken care of that. Otherwise, we're going to get some either undefined behavior or possibly a segmentation fault or something like that. So that's worth bearing in mind. We have to be a little bit careful about that. We then have the copy constructor. Now this simply copies the data from one matrix into another one. So this creates a new matrix essentially and simply copies the data from input matrix. So our input there is input matrix or a reference to it. And we simply call we simply use m underscore matrix data. The ith element of m matrix data is equal to the ith element of m matrix data from input matrix. That's pretty straightforward. And the destructor, we really need that. We just check that if m underscore matrix data is not equal to null PTR, so if something has been defined, then whenever this instance of this class is destroyed, we make sure that we call the delete command here to make sure that we free up the memory that we've allocated in m underscore matrix data. Because we're using the new keyword to define all of this, we're not using anything nice from the standard library. We have to make sure that we take care of this ourselves, and putting that delete command like that in the class destructor should, I believe, take care of that. Okay, so then we have the configuration functions that simply resize. This is really very simple. This simply deletes everything that we have. So it calculates the new, stores the new rows, new columns, calculates the new number of elements, deletes the existing M matrix data, and then reallocates that array to the new size, and then simply goes through and configures all of that to 0. It makes no attempt to copy the data from the previous matrix. To be honest, I can't really envisage any situation where I would want to resize a matrix after creating it. It just felt complete to put that code in, really. So, you know, I guess you could write this to copy some of the elements over, but then you'd have to make decisions about whether you were resizing to larger or smaller, and which elements you kept and which you didn't, and so on. So I think it's just easier to simply to wipe out any existing data, and that returns true if it's successful and false if it isn't. So now we come to the element functions. So these are get element and set element. So the first one that we talk about is get element. It simply accepts as input two integers representing the row and column of the element we want. We use the sub to ind function to calculate our linear index. Let's just skip down and have a look at that. So sub to ind is simply defined here, and it uses the formula that we just talked about in the slide, so row times m underscore n cols plus col to calculate the equivalent linear index for the row and the column, and we just bother to implement a little bit of checking to make sure that row and column are both valid, so they're both less than the number of rows or columns and greater than or equal to 0, and if so we return that value, else we return -1. Really very basic. So let's go back to our element methods, and here we go. So one thing that I notice, if the linear index is greater than or equal to 0, we return M matrix data at linear index, which is of course of type T. Now interestingly, what I haven't bothered to do there is we need to return the value in the case that it doesn't work. So we'll just put return 0.0 there. Okay, so we simply modify that way. That's my fault, I neglected that. Of course, we do need to return something in either case. So if linear index is greater than or equal to 0, i.e. it's a valid index, then we return the element of M underscore matrix data at that index. Otherwise, we simply return 0. Okay. And set element is pretty much the same code, uses sub to ind to calculate our linear index. If the linear index is valid, we set the element of M matrix data indicated by linear index equal to element value and return true, otherwise we return false. Get num rows and get num cols, really obvious. And then we come to the overloaded operators. So the plus operator, really simple, as we just talked about, is simple element by element. So in the condition we have matrix plus matrix. Now we do assume that the two matrices are the same size. It would be more thorough to actually test that, which I haven't bothered to do. I'm assuming that whoever's using this class will know what they're doing, and so the left hand side and right hand side will both be the same size. But simply we calculate, we get the number of rows and number of columns from the left hand side, which we can do because we assume the right hand side is the same, and calculate the number of elements, create a new array here for our temporary result, and then we simply loop through all of the elements and take the ith element of M matrix data for the left hand side and add to that the ith element of M matrix data for the right hand side and store that into the ith element of temp result. Pretty straightforward. And then when we've done that, we finish that for all elements, we create a new instance of QB matrix 2 of type T called result of size num rows num cols, and we store into it temp result. We then delete temp result because we've allocated that ourselves using the new keyword. We make sure to delete it and then we return result, and that's it. So scalar plus matrix, matrix plus scalar are both exactly the same really. So scalar plus matrix there, and this is matrix plus scalar. Actually, I'm just going to modify that a little bit. I would prefer to do it like that. Okay, and so don't really need to say much about those, exactly the same. So the minus operator is of course exactly the same, except the plus sign is replaced with a minus sign, so not much to say there. For the multiply operator, now for constant single value multiplied by a matrix, or a matrix multiplied by a single value, or a scalar times by a matrix, or matrix times by scalar, the code is exactly the same as the code we've just been looking at for addition and subtraction. Okay, so again, I don't really feel there's much need to talk about that. So the matrix times matrix condition is the one that is somewhat more interesting. So here we obviously have two matrices as input, left-hand side and right-hand side, and we then extract from those the number of rows and number of columns on the right-hand side and the number of rows and the number of columns on the left-hand side. And we need to test, it's only really valid to do the matrix multiplication in the condition where the number of columns on the left-hand side is equal to the number of rows on the left-hand side, on the right-hand side, sorry. And if we look back at our slide here, we can see why that is, because we're taking each element here on the left hand side and we're multiplying it by its corresponding element here on the right hand side. So A11 multiplied by B11 plus A12 multiplied by B21 and so on. So we see we need the same number of columns here on the left hand side as we have rows here on the right hand side. Okay, right. Assuming that's the case, we are going to create a new array in which to store our results. So we set up a pointer of type T to an array using the new keyword of left-hand side, so the number of rows on the left-hand side multiplied by the number of columns on the right-hand side. Okay, so again, if we look back at the slide, so the number of rows on the left-hand side is 3, number of columns on the right-hand side in this case is 3, so we're ending up with a 3 by 3 matrix. Okay, and then what we're going to do is simply loop through each row on the left-hand side. Okay, so we're going to loop through each row, so we loop through row 1, then row 2, then row 3. Okay, and for each row we're going to loop through each column on the right hand side. Okay, so for this row we're going to look at this column, then this column, and then this column, and we can see that is that kind of behavior. So for the first row on the left hand side we look through every column on the right hand side, like so. And for that, each there we set a temporary variable called element result we set to 0, and then we're going to loop through each element of the left hand side row. Okay, so we loop through now each individual element of left hand side row, which we can see here, so A11, A12, A13 and A14 in this case. And then for those we calculate the left hand side linear index. Now notice we're not using the intersub function here, we do these within this function because they change a little bit. So the left hand side linear index is simply equal to the left hand side row, so that's from this loop here, multiplied by the number of columns in the left hand side plus the left hand side column, which is from this one. So you can see quite clearly how that's going to work. Yep, that's quite straightforward. Now right hand side linear index is a little bit different. Now here we have to base this on the left hand side column. Okay, so the reason for that is that the linear index here, we're going to go down, say B11, B21, B31, B41, corresponding to each of these. So the column that we're in here, on the considering on the left hand side, will affect exactly which row we want to look at on the right hand side. So what we do that here, we have to take left hand side column multiplied by the number of columns on the right hand side plus the right hand side column. Okay, so left hand side column, so that's 0, 1, 2 or 3, multiplied by the number of columns here, which is 3, so that will give us a 0, 1, 2 or 3, and then add to that right hand side column, which is either going to be 0, 1 or 2 and so on. So you should be able to see how that works from there. And then we cumulatively store our element result. So just have element result plus equals, and then so the relevant element from the left hand side matrix multiplied by the relevant element from the right hand side matrix, calculated using LHS linear index for the left hand side and RHS linear index for the right hand side. And then we simply complete this loop here. So once that loop is complete, we then store that, and we need to store that into a specific place. So we calculate our result linear index, which is from the left hand side row times number of columns on the right hand side plus right hand side column, and then we simply store element result into temp result at that location, and then we complete our second and third loops accordingly, and that will go through and will complete the process for multiplying the two matrices, and then we simply create a QB matrix 2 instance for our result and store into that temp result. Interestingly, for completeness, of course, we should define that of type T. It does work if you don't do that, because I think the compiler can work that out for itself, but I like to be explicit about these things. And then we delete temp result because we finished with it, and we return result. Now in the condition that this is not successful, for example, if this condition here fails, then we simply return a single value result of size 1 by 1, just like that. And the last thing to talk about is we have our code for the equality operator equals, and this works a little bit differently. Oh, one thing I meant to mention is that these functions here are friends of the class. Okay, so you'll notice that the function name here is operator star to overload the multiply operator, and notice that it does not belong to the QB matrix 2 class. So where a function is a member of the class, you would have QB matrix 2 colon colon and then whatever the function name is. So these functions for the overloaded operators are not members of the class, they are friends of the class, as we talked about when we looked at the definition right up at the top. Just really worth bearing that in mind. You can see the difference here because the equality operator we've defined as being a member of the class. So it is QB matrix 2 of type T colon colon operator equals, and then it accepts as input only the right hand side. We're assuming that the calling instance corresponds to the left hand side of the operator. Anyway, this of course returns a type of bool. The first thing we need to do is check if they're the same size. If the matrices are not the same size, then obviously they're not equal, so we simply return false. If they are the same size, we simply loop through, and if we find any, so we initially set a flag to true, and then we loop through every element, and if we find any elements that are different, then we set the flag to false. And that's it. Very simple syntax, and return flag. Okay, so that was the code for the QB matrix class. Sorry, that's quite long. You do see we have nearly 400 lines of code there that we've described, so it is quite lengthy. But this gives us a class that provides all of the sort of really basic arithmetic functionality that we need for dealing with two-dimensional matrices. Now, the last thing to talk about really is how to actually test it. So I have a function here, or a piece of code here, a file I've created called testcode.cpp, and this is going to be the main file that we're going to include. It obviously hash includes qbmatrix.h that we've just been talking about. Here I've using namespace std. I don't normally do that, but because we need to display a lot of output to the terminal, that just saves time. I have a very simple function that I created here called print matrix that simply makes it easy to print out a two-dimensional matrix. So you just call print matrix, specify as input the matrix you want to display, and it will loop through and use cout to display every element. It's pretty basic. For actual testing, the first thing to test is that we can create an instance. So we create a simple array of doubles with 12 values. So that's a 3 by 4. So we store that as test matrix 3 by 4, and then we test that we can print that out. We test that we can retrieve single elements. Notice in particular that we are testing the condition where we try to retrieve an invalid element to make sure that that works. We then test matrix multiplication. We create a new array here, simple data 2, with some different data input, but it's size 4 by 3. And then we display that, and we then calculate the result of test matrix times test matrix 2, and we test matrix 2 times test matrix as well. Okay, we then test multiplication of a column vector by a matrix. Okay, so that's something that we might want to do. We declare a column data with just 3 elements, and we create a matrix of size 3 by 1 with column data, and I've created a square matrix, a 3 by 3 square matrix, to test multiplication with that. So we test initially the column matrix and the square matrix, display those. So we have test column times square matrix times test column, and we also have square matrix 2, which we create as being 1 more than that, because square matrix is defined as the identity, so we add 1 to that just to make it more interesting, and then test that that works with the column vector multiplication as well. We test the equality operator, simply test whether test matrix is equal to test matrix 2, and then we define test matrix 3 to be equal to test matrix and test that. So we test both the negative and positive conditions for that. And then we're testing addition by a scalar. That's pretty obvious. Test matrix plus 2 and 2 plus that, and test matrix minus 2 and 2 minus test matrix, and finally multiplication by a scalar, and that is our test code. Okay, so let's have a look what happens if we run that. So if we go to our terminal window, now I have defined a very simple makefile that deals with compiling that. If we have a look, I mean, this is the code that we have here. We have qbmatrix.h and we have testcode.cpp. The makefile, I mean, it's equivalent to just doing g++ on testcode.cpp, to be honest. So, I mean, that's pretty straightforward. If we now run that, /testcode, and let's just go through and have a look at the output. So we run that here. So first of all, we created our 3 by 4 test matrix called test matrix, and you see there it is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that was defined, as you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that shows how the linear arrays are translated into 2 dimensions there. We test element retrieval. We test retrieving element 0, 0, which is of course 1, element 1, 0, which is 5, element 2, 0, which is 9, 0, 1, which is 2, 0, 1, 1, which is 6, and 2, 1, which is 10, and 5, 5, which of course is invalid, returns 0. We then define test matrix 2, which is 4 by 3, so consisting just of 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And we test multiplication test matrix multiplied by test matrix 2, which gives this result, which I believe to be correct. And test matrix 2 multiplied by test matrix, if we do it the other way around, we then get a 4 by 4. So, yep, that's fine. Again, I've tested these by comparing with the output from other software, and I do believe those to be correct. Of course, as I stressed in the introduction, very important if you want to use this code for anything, do test it yourself. I can't emphasize that enough. I obviously can't provide any guarantees. I do everything I can to make sure I don't make any mistakes with my code, but it's always possible that I have. So absolutely do test it yourself if you want to use it for anything, just to make sure it works as it should. Indeed, if you find any problems with it, do please let me know in the comments below. I'll say we test multiplication of a column vector by the matrix. So we define our column vector here, 3 elements, and we define our square matrix as the identity matrix, and we have column vector times square matrix is invalid, returns 0, but square matrix times column vector we can do, and because that's the identity vector, the output is the same. We then add 1 to our square matrix to make it a bit different, and then do square matrix plus 1 times column vector, which we see now gives 9, 10, and 11, which is indeed the right answer. And we test the equality operator. Obviously, test matrix equals test matrix 2 is obviously false. Test matrix 2 equal test matrix, obviously false. And then we let test matrix 3 equal test matrix, and we test those at positive conditions. And then obviously we have addition by scalar, so test matrix plus 2, that is correct. Yep, 2 plus test matrix is obviously the same. This is, apologies, a mistake there. This is subtraction by a scalar, so test matrix minus 2 is obviously there. Yep, and 2 minus test matrix is that. Yep, so there we go. And finally, we have multiplication by a scalar, so test matrix times 2 obviously gives that, and 2 times that is the same. So there we go. We see, according to those tests, which I think are reasonably exhaustive, that it does appear that the code is functioning as it should. So that did take quite a long time to go through, but we've seen the code that we need to use to create a simple class that implements matrices and allows us to work with 2-dimensional matrices in terms of basic matrix arithmetic. So there we go. That's really everything that I wanted to talk about today. We've looked at the basics of matrix arithmetic in terms of addition, subtraction, and multiplication, and I've gone over the code that I've created to implement a very simple class to allow us to work with 2-dimensional matrices in terms of those operators in C++. I think we've covered enough ground for today. In subsequent videos, I want to go on to build on this basic functionality that we've done today, and also I want to go on to actually use the matrix class that we've created to do some interesting things. So my personal interest in using 2-dimensional matrices is to be able to do image transforms. So we're going to come on to that in a few videos time, and hopefully that will be of interest. But I think for today, we've definitely covered enough ground. So we will see what comes next in future videos. It does leave me to say, as I always do, that I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have enjoyed it, please remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Anyway, listen, it's been a pleasure. I really hope you've enjoyed the video. Thank you very much for watching. Bye.